always treat this simplex as a yeah, so even though the definition of the boundary operator depends on an orientation, the homology group turns out to be independent of it, of what orientation we set up. Mostly because like you're taking sums with coefficients in Z. So like if the boundary operation acting on a particular simplex gives you a specific sequence of signs, you can always multiply it by -1 and get the opposite sequence of signs. So we need to compute, first of all, Z0, which is nothing but C0 because there are no zero-dimensional boundaries. So this is just going to be Z to the N. We also have, well, actually, oh, sorry. There are no -1 dimensional boundaries. Sorry. B0 is the space of zero chains, i.e. space of formal sums I, Ci, Ei, such that sum over Ci is equal to 0. Because you want this to be a zero-dimensional boundary, which means you want it to be the boundary of some sort of you have a linear combination of zero simplices, and the boundary operator basically multiplies each coefficient by +1 and just adds them together, which means that you get this constraint for a zero-dimensional boundary. And this, because of that constraint, this is isomorphic to Z to the N-1. C1 similarly is the space of linear combinations Ci, Si, where Si is given by these. With the coefficients in integers, this is isomorphic to Zn. B1, on the other hand, is 0, the space of one-dimensional boundaries. Z1 is the space of one chains, Ci, Si, such that, again, by using this boundary, the definition of the boundary operator, such that Ci minus Ci plus 1 is equal to 0 for all I. So this is N-1 constraints on N numbers, which means that this is isomorphic to Z. What is the chain that generates this?
Can we just take
from, what do you mean, constant maps from?
Yeah, you can spread one chain is just finding value to every one simplex, and the difference between values of
Yeah. But there's still one free number here. Yeah, exactly. And so the chain that generates this Z is basically just the boundary of this polygon because the interior is not included. So it's just that particular set. So you can say that this is generated by sum over I Si, which corresponds to concatenating all the boundaries together, all the edges together, which is the full boundary. Okay, so we have all of these groups, which implies that H0 is isomorphic to Z to the N, which is Z0 mod Z to the N-1, which is B0. And this is Z. Similarly, H1 is isomorphic to just Z1 mod B1, but B1 is 0. So it's just Z1, which is Z. So note that this has rank 1 as an abelian group. This has rank 1 as well. Sorry, as a free abelian group. And recall that the de Rham cohomology of NS1 was also given by R if P is equal to 0 or 1, and 0 otherwise. So the dimension of the de-Rham cohomology of a circle is the same as the rank of the homology groups of the circle, of this triangulation of the circle. And this is like actually a general fact for manifolds, that the de-Rham cohomology of M is isomorphic to the simplicial homology of M with coefficients in R. So if you compute this homology group with coefficients in R instead of Z, you'll find that this is R and this is also R, and all the higher homology groups are 0. For M, a smooth manifold. All right, so that was example 1. Example 2, a tetrahedron, which can be taken as a triangulation of S2. So when I say tetrahedron, I mean the faces of the tetrahedron that don't include the interior, the union of all its faces and edges and vertices, but not the interior. So you can convince yourself that so you want to look for cycles that aren't boundaries, and you can convince yourself that the only such cycle is the union of all its faces, because the interior is not included, which means that H0 is always going to be Z, H1 is 0 because there's no non-trivial one cycle, and H2 is going to be Z as well. So it's generated by the union of the faces, or just the sum of the faces. Example 3 is that of a Mobius band. So you can triangulate the Mobius band as follows. Mobius band is basically a strip with opposite ends identified in an opposite way. You can triangulate this in the following way. H0 as always is going to be Z. H2 is 0 because that's just a general property of p-dimensional simplices. H1, what is this going to be? Because there's no, well, one sec. No, sorry, that's not true. Oh, because there's no, well, the only, each of the two-dimensional simplices are themselves, one sec, let's see what's the best way to say this.
I mean, the only way to actually show this to you.
Yeah. 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 Exactly. Yeah. What about H1? So you need some sort of loop in this space, in this triangulation that isn't a boundary. Can you find one? So if it was a boundary, that loop would be contractible within the Mobius band. But you can always, because this end is identified with this end, you can consider this. Yeah. Yeah, you can consider this loop, or just take the one on the top. And you can see that because this cannot be contracted down to a point while staying within the Mobius band, it cannot be the boundary of any two simplex. So this is going to be Z as well.
The same generator as this.
Yeah.
I was going to say, doesn't that also follow Alex's comment? This is from the topic.
Yeah, exactly. So the reason I wanted to explain this is because you can, like, based on this argument, this the whole argument is sort of very similar to what we did for fundamental groups. When we look, the fundamental group was basically just the space of loops that aren't contractible down to a point. And so this sort of motivates a relation between the nth homology group and the nth homotopy group, because you can always think of it in a very similar way, and there's a more precise correspondence that we'll get to. But you can think of there is a way of thinking of homology groups in terms of non-contractible loops and cycles as well.
Being a boundary of something is not the same as being
Yeah. Yeah.
You can distinguish fewer spaces.
Yeah.
If you are contractible, then of course you sweep out a surface of which you are the boundary.
Exactly.
But if you are a boundary of something, then that's something you can get contracted.
Exactly.
You're saying homology is giving lots of information.
Yeah.
Is it to do with homotopy invariant but not isomorphic? The fundamental rule is you can get not
Homomorphism invariant, you mean?
well, everything's homomorphic.
Yeah. Oh, yeah. Wait.
If you can get not invariants out of the fundamental group, you can't get them out of the drum.
Mm,
Homotopy groups are also
anyway. But yeah, so the more precise statement of that, for instance, for the fundamental group would be that the first homology group is the abelianization of the fundamental group. But we'll get to that. Similarly, if you have RP2, which is isomorphic to a disk with antipodal points identified, you can triangulate it like this. So this point is identified with this one, this is identified with this is identified with this, and these 3 points are distinct. So once again, H2 is 0. H1, on the other hand, is given by Z2, which is Z mod 2Z. And the reason this is true is because you have like a non-contractible loop. It goes like this, for instance. So it generates a non-trivial first homology group, but traversing twice along this loop will bring you back, will give you a contractible loop. So taking it, so this loop, when added to itself, becomes a boundary. Oh, sorry, not this. Wait. Ah, yeah. One sec. Yeah. Yeah. So if you traverse twice around the same loop, it becomes contractible, which means that the corresponding simplex, the corresponding chain added to itself is now a boundary.
But it's much more clear. This, right? Go like this.
Yeah.
Then if you repeat this twice, that's the same as going all the way, right? Which is obviously contractible.
Yeah. So those are some examples. We have a definition next, which is Betti numbers. So suppose K is some finite dimensional simplicial complex. By the fundamental theorem of finitely generated abelian groups. Every finitely generated abelian group can be written as a free part, which is Z to some BPK. and direct sum with a bunch of twisted groups. Okay. So this is called the free part, and this is called the torsion. And the exponent of the free part is always going to be positive. These are called the Betti numbers.
This is only one time when
Yeah, exactly. Yeah. All right. So when you, on the other hand, when you take this group and tensor it with some field that contains at least the rationals, the torsion part disappears. So HPK tensored with Q gives you Q to the BPK. And now this becomes a Q vector space. And then the Betti numbers are basically the dimension of this Q vector space. We'll later show that if K is a triangulation of some manifold, then the Betti numbers are also given by the dimension of the DRAM cohomology of M. Another way of saying that is because the DRAM cohomology is isomorphic to the simplicial cohomology with coefficients in R. So instead of tensoring with Q, if you tensor with R, you get R to the BPK. And as a vector space, that's just a BPK would just be the dimension of that. Oh, yeah. So the reason torsion disappears when you multiply by Q is, for instance, if you take Z M1 tensor Q, suppose you, let's just call this M. Suppose you take an element A in here and an element B in here. A tensor B is equal to MA tensor B over M by linearity. But MA in Zm is identified to be 1. Yeah, depending on what notation you're using. I usually use the power notation for cyclic groups, so, but yeah. Or A to the 0 or whatever. Yeah, so whenever you tensor, because Q contains all of the inverses of every cyclic group you can define, tensoring with Q always gives you a trivial group. Or a trivial vector space.
you can multiply by any field. So the smallest one.
Yeah. Was that?
If you are looking at complex over Z mod Q, then
No, we just have integer.
Yeah.
but you can find this for any alien group.
Yeah.
So you ensure taking coefficient from integers, you can take over portion of it. And then to do this, you just instead of taking all the rest, you can say the finite group.
Yeah, exactly. Now the definition. This is a first example of a characteristic class.
The Z coefficients are basically, if you know Z, if you know homology of the Z coefficients, then you know any other coefficients. Because Z is the initial logic.
So suppose, once again, K is an n-dimensional. I'm just going to write SC for simplicial complex. I don't want to write the whole thing again and again. So we have two definitions of the Euler characteristic. The first one is chi of K is defined as sum over p from 0 to n, minus 1 to the p, np of k, where this is the number of, is the full thing on, is the full board part of the screen, or do I need to?
Just up to the yellow thing.
Okay. This is the number of p simplices. This is called the combinatorial Euler characteristic. Alternately, there's another definition. Chi of k is sum over p from 0 to n minus 1 to the p times the Betti numbers.
The one Euler you-
Yeah. This is equivalent to the vertices minus edges plus faces up to some minus 1 to whatever factors. Yeah, so this is called the homological Euler characteristic. And the theorem is that both of these are equivalent. The two definitions are equivalent. And in particular, since the Betti numbers are homotopy invariant, because the homology group is, so is the Euler characteristic. All right, proof.
Which was the original Euler's observation, right? That all regular quantities are
Yeah.
just even though it's not obvious.
Exactly. All right. Yeah, so consider just the free part of the chain complexes, the chain groups, by tensor with rationals. So this forms a Q vector space. The boundary operator on these groups is a map from k comma q into cp minus 1 of k comma q. This is a linear operator on these Q vector spaces. So we can use the rank nullity theorem to conclude that NP of k is the dimension of Cp of k comma q, which is the dimension of kernel of dp plus dimension of image of dp. Similarly, yeah.
But it's also
Cool.
But why is that to conclude that? Isn't that
there's a whole statement that formula that seems
isn't the chain complex that we define each space is generated by simply the formula?
Yeah.
So that dimension has to be in the after cancel.
Yeah. Pretty.
You don't need random.
Well, I mean, rank nullity is equivalent to saying that. So all you're doing is you don't need rank nullity for the first equality, but you need it for the second one. And it's the second one that'll be useful to equate the two. So on the other hand, BP of k was the dimension of ZP of k mod capital BP of k. So this is the dimension of kernel of dp minus dimension of image of dp plus 1. So once you have this expression for NP and this expression for dp, you can take these alternating sums and see that they're both equivalent. This implies that combinatorial chi is equal to homological chi. Yeah. Okay. So with this, we're going to sort of take a short aside and go back to DRAM cohomology for a bit. So there's a result about the finite dimensionality of DRAM cohomology groups that we prove for a specific but pretty large class of manifolds. And assuming that we take open covers of the manifolds appropriately, we can prove that the dimension of the DRAM cohomology group, DRAM cohomology vector space of these manifolds is always finite.
Let me say, so there's a basic idea here. Which is, like, remember when we talked about the classification of microbundles, we had, like, with a given structure group, it was enough to basically cover the base with small open sets and then only classify the cosets. On the intersections of those open sets. And that way, up to homotyping, that way you classify all microbundles. So basically, everything comes down to these little intersections of open sets. So the same idea here, where we have a migratory sequence, which tells you then we can give homologies of unions of open sets if you know the homologies of their intersections, for instance, and you keep them separately. But that means that you can have M equal U union B, just cover the manifold by two sets, and then you have migratory sequence. But and you can imagine applying this iteratively to smaller and smaller sets, assuming that you somehow know all of the homologies in every step and the exact sequences of their values. Then, like in principle, you can use migratory like arguments to compute homology of any manifold by picking a sufficiently fine cover by open sets, right? And then using for each open set, you can assume it's contractible if it's small enough. And then for that, you just use Poincare limits to say homology is zero. Right? And everything else is in there using migratory.
So you just make it fine enough and then basically use stitching on the overlaps too.
Yeah. Exactly. So we start with a definition, which is that of a good cover. So suppose we have a collection of open sets that's an open cover of a manifold M, which is n-dimensional. So this is a good cover if all non-empty finite intersections U alpha 1 dot 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 alpha k is given by yeah. Yeah. So if all such finite intersections of elements, open sets of this open cover are diffeomorphic to Rn, or in other words, contractible. Proposition: every smooth manifold has a good cover. The proof of this is sort of straightforward. So recall that every manifold admits a Riemannian metric. Yeah, it's proved by appealing to something more complex. It's proof by appealing to something more complex, so it's praying. Right. Every manifold admits a Riemannian metric, and every Riemannian metric Riemannian manifold can be covered by geodesically convex open neighborhoods. Similarly, intersections of, so once we have this open cover by geodesically convex open neighborhoods, intersections of geodesically convex open neighborhoods are also geodesically convex open neighborhoods, which means that we have a good cover. They're geodesically convex, so they're diffeomorphic to Rn. Yeah, I mean, if you want the diffeomorphism, just take the geodesic that connects, pick a point and take the geodesic that connects it to every other point. You can map it back, contract it along that map. Great. So recall that a collection V is a refinement. An open cover V is a refinement of an open cover U if every element of V is contained in an element of U. Or some alpha. All right. So the this is usually denoted by U less than or equal to V. Corollary is that of the previous proposition is that every open cover has a good refinement. So as a refinement, that is also a good cover.
Which is taking cover and take this intersection.
Yeah, with all sets in the geodesic convex cover. All right. One more definition. Well, technically two definitions in one, but directed and cofinal sets. For a long time, I used to think this was confined. So a directed set is a set I with a relation less than or equal to, such that the following properties hold. You have reflexivity, i.e. A is less than or equal to A for all A. Transitivity, i.e. A less than equal to B and B less than equal to C implies A less than equal to C. And finally, an upper bound, i.e. for all A comma B in I, there exists a C in I such that A is less than equal to C and B is less than equal to C. So this is the definition of a directed set.
Confirm that A less than or equal to B and B C does not imply that B.
Yeah.
So that's the difference from
Yeah. So J, a subset of this directed set is called cofinal in I. If for all I in I, there exists a j in j such that I is less than or equal to j. So by this property, j is automatically a directed set in itself. All right. Yeah. So so in particular, this definition implies that the set of open covers of a manifold is directed, and the set of good covers of M is cofinal in this directed set. So this corollary can be restated as saying that the set of good covers of M is cofinal in the set of open covers.
So if we put other ways to make sufficiently nice in the same language,
Like, what do you mean by sufficiently nice?
like what we find out and whatnot, that you frequently require. Oh, you can require whatever you want. Yeah, you want.
Yeah. I mean, I don't know if there exists a relation. So this is in particular with respect to the relation of refinement. So maybe if you can construct a relation where like locally finite becomes a cofinal set in the set of open covers, I guess, but not with this relation. Okay, proposition. Yeah, so if,
By the way, these are also categories, right? So you can see, remember how every partially ordered set goes in that category? Directed sets are generalization. These are also categories. Because all you need for this to be a category is transitivity of the perfect set.
yeah, you don't need the upper bound.
Yeah, so this means that you can take direct limits.
Yeah.
And you can take infinite sequences, take direct limits. You have a cofinal set. This is basically saying that every direct limit will lie in a
All right. So proposition: if a smooth manifold M has a finite good cover, then the de Rham cohomology is finite dimensional. So this may be with or without compact support. So this is finite dimensional. So in particular, this holds for every compact manifold, because by definition, if you have an open cover of a compact manifold, you can reduce it to a finite subcover, then have a good refinement of that. Or if you have a good cover of a compact manifold, you can reduce it to a finite subcover, and you can show that it's also going to be a good cover, which means that the de Rham cohomology will be finite dimensional. Take Rn and cover it by 2 Rn minus 1s. So like,
it depends on how you construct that.
yeah.
You know, every manifold has to be defined. So you look at the chart, or you look, maybe your manifold was just you took some compact manifold and you glued it into another.
Yeah.
So like really depends on how you
Exactly. Right. So to prove this from the Meyer-Vittorius sequence, you have this following long exact sequence in cohomology: -1 U intersection V delta HQ U union V R HQ U direct sum HQ V and dot dot dot. Was that? Ah. All right. So by the rank nullity theorem, we also have HDR Q U union V is isomorphic to kernel R, direct sum image R, where this is the map R. And because this is an exact sequence, this is isomorphic to image delta direct sum image R. So in particular, if this is finite dimensional and this is finite dimensional, so is this. So if HQ U HQ V and HQ minus 1 U intersection V are finite dimensional, so is HQ U union V. So this is when you have a union of two sets. To prove this for general manifolds, you can proceed by induction. For the base case, you just have Poincare lemma. That's induction in the number of sets covering the manifold in the cover. For the base case, you just have Poincare lemma that states that it's true in size of good cover. Yeah. Yeah. Exactly. All right. So we assume that the cohomology of any manifold with a good cover with at most p elements is finite dimensional. And consider a manifold with a good cover given by a collection U0 dot 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 UP of P plus 1 open sets. By the induction hypothesis, we have that the following set U0 union UP minus 1 intersection UP. This has a good cover with this set or this manifold has a good cover with p elements. Basically, this good cover is given by taking the intersection of UP, which each of these elements, so U0P, comma, UP minus 1P. So by our induction hypothesis, hold on, let me call this thing BP. So by induction hypothesis, HDR of VP intersection QP is finite dimensional. So is HDR of UP and HDR of VP, because VP itself is a union of P open sets, which themselves form a good cupboard for it. P minus, yeah, P open sets. So using the Meyer-Vittori sequence argument, the DRAM cohomology of UP union PP, which is basically M, is also finite dimensional. All right. Finite type. Okay. All right. Say that again. Right. Okay. So we'll compute the homology groups of the n spheres. Note that you can write any n sphere as a union of two of its hemispheres, where each of u, v are diffeomorphic to Rn hemispheres. U intersection v is diffeomorphic to Sn minus 1 Cartesian product with the real line, which is homotopy equivalent to Sn minus 1. So we can write down the Meyer-Vittori sequence. Hp minus 1 Rn, direct sum Hp minus 1 Rn for u and v individually, maps to Hp minus 1 Sn minus 1. I should write this. There's an Hp minus 1 Sn here. Actually, yeah, this is not important, whatever. Maps to Hp of Sn, which maps to the same thing with p instead of p minus 1. So in particular, if p minus 1, I'll write it on a new board. So in particular, if p minus 1 is greater than or equal to 1, so p greater than or equal to 2, this is the homology group of Rn with index with degree greater than or equal to 1 is always trivial. So you get a short, well, not short, rather shorter than short exact sequence of the form. Now, exactness implies that this basically has to be a bijection between the homology groups, which implies that Hp minus 1 Sn minus 1 is isomorphic to Hp Sn. So we have a recursion relation for the homology groups that goes as long as p is greater than or equal to 2. Solving this recursion relation essentially gives us the following. HDR Rn Sn is equal to R if p is equal to 0 or n, and 0 if p is not equal to n. For the p equal to 0 case, this the short exact sequence isn't valid anymore because this is non-zero. So you have to work it out a little more carefully. But h minus 1 of any manifold is always 0, so you get a slightly longer exact sequence that you have to work through to get.
It's just you go down to n equals 1, you get right.
Yeah.
Hn of H0 of a point is R.
Yeah. No, but like this recursion relation doesn't hold then. So you can't extend that recursion relation. Yeah. Yeah, pretty much. So, yeah, sorry, for p equal to 1, you have to do a little more non-trivial stuff, because in that case, this is non-zero, but this is 0. So you get a short exact sequence then. Yeah, p equals 0 is trivial. So this ends the detour. Oh, also one more thing. So we have,
Oh, yeah, S0 is 2 points, right? That's why there's
right. Yeah.
so M0 to 0, then actually are 2, but there's an extra R in the sequence somewhere.
Yeah, exactly. All right. So we have the Meyer-Vittori sequence as a really powerful tool for computing DRAM cohomologies of real manifolds by just decomposing them into a union of two manifolds that are whose intersection is known in terms of the cohomologies. But you can ask if you can do something similar for Dolbeault cohomology for complex manifolds, and the answer is that there is no Meyer-Vittori sequence for that. And the reason being that in order to define this sequence properly, in order to define this decomposition, you had to restrict differential forms to a particular subset by using bump functions. But bump functions are not holomorphic, because by analytic continuation, if a holomorphic function is 0 somewhere, it's 0 everywhere, which means that you can never define this bump function, and you can't have this decomposition because of that.
This is why we need smarter cohomology.
Yep. All right. So we'll move on to like slightly more abstract analyses of homology groups and how to construct them in a general abelian category. Definition. So a co-chain complex or a chain complex so usually denoted by, so for chain complexes, usually denoted by a double C with a dot below it, P, in an abelian category.
Mom, it seems like a habit when you write it in a notebook, there's a white space on the left. There's like a half a meter white space in every.
I guess, yeah. I'll draw a margin. Yeah, so in an abelian category C, this chain complex is defined as a sequence of morphisms. And of course, the sequence of objects as well. It goes like this: dn plus 1, cn, dn, cn minus 1, dot, 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 where the index n is an integer, such that dn composed with dn plus 1 is 0. Similarly, we also have cochain complexes. Which really are not any different from chain complexes, but we still define them separately. Which is the sequence C n minus 1 d n minus 1 C n d n. Yeah, exactly. So usually chain complexes are only those chain complexes are considered where this truncates at n equals 0. And for those that are indexed by negative integers, you can always flip them and define a cochain complex accordingly. Such that dn plus 1 composed with dn is 0. This is basically just n going to minus n on the chain complex. Yeah, dn composed with dn minus 1 or dn plus 1 composed with dn. Same thing. Yeah. Right. So basically, because there's just the same as a chain complex with indexes reversed, we only need to prove any theorem for chain complexes, and we can forget about cochain complexes until we actually do examples. Then cochain complexes matter. All right. So a definition of cycles, boundaries, homologies of complexes. So suppose we have a chain complex, which I'm going to write as CC, given by C dot D. N cycles are defined as Zn C dot D equal to kernel of Dn, and boundaries are defined as Bn with the same arguments, equal to image of Dn plus 1, and the nth homology groups Hn C dot D is equal to Zn mod Dn. Yeah, for the chain complex, not the cochain complex. On the other hand, if you have a cochain complex, yeah, just flip the indices. Definition, chain map. So suppose B comma delta and C comma D are two chain complexes. A chain map is a map F from B to C, or rather a sequence of maps between each object of the chain complexes. Such that Dn composed with Fn is equal to Fn minus 1 composed with delta n. So basically all the squares commute. Fn All right, and similarly cochain maps as well. Proposition. Right. So suppose we take the collection of all chain complexes in an abelian category C with the set of chain maps between two complexes. We get another abelian category called comp C. Which is the category of complexes in C. So the proof of this is just done by checking if this category obeys all the definitions, the properties of the axioms of an abelian category. So first of all, by Freyd-Mitchell theorem, every abelian category can be embedded into the category of R modules for a given R. So we only need to prove this for R modules. And in this, for C equal to R mod, this structure is kind of obvious. So the zero object in comp R modules is the zero complex. Um, direct sums in this category are defined by taking direct sums in each degree. Oh, this index in the chain complex is called the degree of the corresponding object. So you can just, to take the direct sum of two complexes, just take the direct sum of each object at a particular degree, and the maps as well. Kernel and co-kernel are basically complexes that consist of kernel Fn and similarly co-kernel Fn. Image and
And we had, remember the first moment, the first diagram chasing, you have a map, then it induces a map between kernels.
Yeah.
We know what to write in the complex consisting of kernels.
well, and especially if you, because you're working in RMod, it's much simpler. That's, I mean, in fact, like it's only because you work in RMod that you can do diagram chasing, right? So like Fred-Mitchell theorem is essential for that, for all those lemmas. All right, so images and co-images coincide since
I mean, there's this work if I know that it's again I do this.
well, no, not for this, for diagram chasing.
I mean, what we're using.
Yeah, so
We're just referring to other results that they also proved in our modules and then said, okay, well,
yeah, exactly. But like for diagram chasing, you need concrete categories. So like you need the Fred-Mitchell theorem to hold for that, because you need to have objects as sets.
anyway, yeah.
Yeah. Okay, so we've checked that comp C basically obeys all the properties of an abelian category, so it's an abelian category. So positive complexes. So, oof. What? Where is it useful? See, that's so much better than N category hyperhomologies. Homologies. That works. We should write a paper.
No, but then it's like chemistry, you end up counting syllables.
Okay. So a chain complex. So when I'm not referring to D, I'm going to use a single underline to denote a chain complex. There's no good way of doing this. Okay. See bullet. So this is said to be positive if Cn is equal to 0 for all n less than 0. So basically, and this forms a full subcategory of comp C. Positive chain complexes form a full subcategory denoted by comp greater than equal to 0. C, yep, which is also abelian. So basically, you get chains of the type C2, C1, C0, and 0.
category of complexes, the opposite of the category of complexes is the same as complexes is the opposite category.
What?
Or co-complex.
Yeah. Yeah. So you can have negative complexes similarly of the form 0, C0, C1 dot dot dot, and C minus 1 dot dot dot. And these are basically just equivalent to cochain complexes by just relabeling everything, the index to its negative value. Hmm? Yeah. Right. Okay, so one more proposition. So suppose C is an abelian category, then the nth homology group, or just nth homology, is a functor from comp C into C. And more than that, it is an additive functor. It is an additive functor. Additive covariant functor. So additive just means that it's an abelian group homomorphism on each Hom set. Right. So, and obviously, if you look at the nth cohomology, it's going to be an additive contravariant functor. Proof. So, given a chain map, so basically we already know in C complexes need to construct a morphism Hn of F that takes Hn of A to Hn of C. So because Hn of A is given by Zn of A mod Bn of A, we can try and do the following. Suppose we take some point Z, some element Z in Zn of A, such that the map Fn from Zn of A into Cn, which is the nth object in this chain complex, takes Z to Fn of Z. And we can try and define the map Hn of F from Hn of A to Hn of C as taking, so this would be an equivalence class of Z in the nth homology, and this maps into the equivalence class of Fn of Z. Yeah. Oh, yeah, sorry. Yeah, which is what we'll do. Yeah, so these equivalence classes are with respect to quotients in like BNA and BNC respectively. And I'm going to use the same notation for the chain, not the chain map. What's the D called? Is there a word for it? The differential in. Yeah, the boundary. I'm going to use the same symbol for the boundary operator. So what we need to do is need to check that Fn of Z basically belongs in Zn of C. Otherwise, this equivalence class doesn't really make sense. It's not an element of Hn of C. Why indeed? Exactly. And that's true because dn of Fn of Z is equal to Fn minus 1 of dn of Z, which is 0. So Fn of Z is in Zn of C. I can't believe I managed to say that sentence without breaking up. Okay, since Z is in Bn of A, wait, Zn of C, yeah, I just said that, I'm not gonna write that down. Furthermore, we also need to check independence of the choice of representative. Of the equivalence class of Z. Yeah. So suppose Z and Z prime are elements of Zn of A such that they have the same equivalence classes in the homology, which is the same as saying that Z minus Z prime belongs to Bn of A. All right, then there exists a Y in An plus 1 such that Dn plus 1 of Y is equal to Z minus Z prime by this, which implies that Dn plus 1 of Fn plus 1 of Y is equal to Fn of Z minus Fn of Z prime, because F and D commute, which implies that this is this thing is a boundary, which means that this map is independent of the choice of representative. The last thing to do is check functoriality. I.e., check that this functor obeys the composition property. So suppose we have complexes A, C, and D. It maps F and G. Dot, dot, dot. We need to show commutativity of the following triangle. This is Hn of F. This is Hn of G. This is Hn of Goff. So to do this, we take Hn of Goff of equivalence class of Z. This, by definition of Hn, is equal to G composed Fn of Z with the equivalence class of this object. Splitting this up, this is equal to the equivalence class of Gn composed with Fn of Z, which is equal to Hn of G acting on the equivalence class of Fn of Z. Then do the same thing over here again. So this is Hn of G acting on Hn of F acting on the equivalence class of Z, which is equal to, well, we just shown that this commutes. So, and one last check is additivity. This is trivial because Fn are homomorphisms. So Hn of f plus f prime is going to be equal to Hn of f plus Hn of f prime. So we'll write f lower star for Hn of f and g upper star for the corresponding cohomology functor for the descendants of maps in cohomology or in homology. That's my reaction every time I learn category theory. The connecting homomorphism lemma. No, zigzag is next. Zigzag is next. Well, sort of. Basically, zigzag involves this. So suppose we have a short exact sequence of chain complexes. No, it should be called zigzag. So there's a short exact sequence of chain complexes. The statement is that for each n, there exists a connecting homomorphism given by delta or delta n, which is a map from Hn of C, the nth homology group in C, to the n minus 1th n minus. I'm going Greek now. N minus 1th. N minus 1th cohomology group of A. That basically goes like this. Takes the equivalence class of a cycle Z, equivalence class of the following object. Don't ask me what this means. I'll explain it in a second. I n minus 1 inverse dn pi n inverse of Z. Aha. Time to do some diagram chasing. Would you chase a snake or would the snake chase you?
Depends on how much I like this thing. When you're doing diagram chasing,
Good question.
I'd like to fix the diagram.
So we basically need a bunch of checks for this. Number one, y is dn pi n inverse of z in the image of I n minus 1 to make sense of this expression. Okay, let me draw this diagram. I'm just going to use, again, the same symbol for both of these. So suppose we have an element here, Z. Suppose we pick Y in B. such that, yeah, because pi is surjective, there exists a y in B such that z is equal to pi n of y. Yeah, so you'll have an element here, dn of y in Bn minus 1. Now, furthermore, since z is an element of Zn of C, we have the following: pi n minus 1 dn y is, so you're looking at the image of dn y under this map, is equal to dn pi n y by the commutativity, and this is dn of z, which is 0 because z is a cycle. So this maps to 0 in here, which means that dny is in the kernel of pi n minus 1, which is the same as the image of I n minus 1, which implies that there exists an x in a n minus 1 that maps into here. And we have, there exists uniquely an x. And we have a well-defined map that takes z to x. Fun diagram chasing. Yeah, exactly. So the second thing is, and this is something I'm not going to do, but we also need to verify that x is in Hn minus 1 of A. It's not. I don't think it is. I think you need some more diagram chasing to do that.
So we also need to do the same that we're constructing maps, boundaries, and boundaries.
Can you say that again?
So we just need to show that this map has boundaries in Cn, boundaries in An minus 1.
Yeah. So we need to check this. We also need to check that this is independent of choice of y and independent of choice of representative of this equivalence class of z, which I'm not going to do because I want to get the zigzag. Yeah. This is the lemma we used for even for like the generating the long exact sequences in the Mayer-Vitoris sequence for DRAM cohomology theorem. Finally, here.
Apparently, a lot of people call this a snake molecule.
I mean, snake is zigzag. All right. So the statement is that for all short, exact, I might end early today, sequences of complexes, 0, a dot.
You just generate this for the sheet. And this is a derived construction.
Yeah.
But since abelian is R mod, so this one.
Exactly.
Even if it's not R mod, you can
Yeah. You can always just work in R mod insert by Friedman. So.
maybe.
Yeah, for abelian categories. Oh yeah, sheaf homology is slightly different. Yeah.
But you can
Where
still
can
have,
we do it? Chief?
but you can have like derived from the non-abelian. Using like
Mm. Right. So for this short exact sequence of complexes, the induced sequence in homologies given by yep. Oh, whoops, my bad. Yeah. I think you need to make a correction in the diagram in your notes. Yeah, I think so. Yeah. This is exact. So we got a long exact sequence in homology. Yeah, this is going to be delta n plus 1. This is delta n. Proof. Okay, so I'm going to write down a whole bunch of sequences that are short exact and use them to construct this long exact sequence, show that this sequence is long exact using snake lemma. So we have two fundamental sequences for every complex C. The sequences are given by 0, Zn, C, Cn, B, n minus 1, C, 0. Let me call this 1. There's another one, 0, Pn, C, Zn, C, Hn, C, 0. This one is exact trivially because Hn is just Zn mod Bn. And so is this one because Bn minus 1 is just Cn mod Zn. There's 2. These are short exact.
But the first one, that's by
Yeah, by the first isomorphism theorem. Yeah. So is the sequence 0, PNC, CN, CN mod BNC, 0. So using the exactness of the first one, we also have this exact sequence. Where this thing is isomorphic to Cn mod ZnC. Call this 3 using let's see. Oh, it's sort of just taking the sequence and taking the sequence and modding out these two by B and C. This is still going to be surjective because if every object here has a preimage here in Cn, then every object here has a preimage in this quotient. This is injective because you've just quotiented both sides by B and C. So now we can take sequence 2 and sequence 3 and put them together because they have this common HN here.
So if you define HN using the second chain, like you just HN, you define HN to be this,
Uh-huh.
wouldn't thinking that be become trivial? Like that it's a function, you define HN to be this object. Instead of like, because that is just like your coconut, right? That's just mapping. So given a sequence of chain maps, you're mapping everything to its coconut. And you don't really have to check if that lies in the main chain that it is.
Johnson Jones statement that is something different. It's defined as an element of the defense against the
All right, so we can use sequence 2 and sequence 3 and use the fact that they have a common HN there and put them together to get this exact sequence, which is not short. HNC. Wait, sorry, not a common HN. The fact that they have a common BN and BN minus 1 maps into CN mod BNC. Maps into, so I've taken the first two elements here, use the fact that this is this to construct a map from Cn mod Bn to Cn to Cn minus 1. Wait, did I? Oh, sorry, I'm looking at the wrong sequence. All right, I'm going to rewrite this as n minus 1, n minus 1, n minus 1. So start with this sequence. Bn minus 1 naturally maps into Zn minus 1, so we can concatenate these two maps to get a map from Cn mod Bn to Zn minus 1 and end with that sequence. So this is also exact. So we can use, there'll be such a sequence for the chain complex A, the chain complex B, and the chain complex C. And we can use these as the columns of one giant diagram. That looks like this. It's going to take a while. It's sort of unfortunate that I'm using B here for the sequence, but like it's clear from context, right? What Bn is and what Bn of B is. Just because that's how it's done in books doesn't mean that's good.
They are different. It's not like we've exhausted the Roman alphabet. When the n is an element of the chain complex B, it can't be a function of it. We'll never think of it that way.
Sure. See, this is why it's confusing. Yep. Okay. So we have this horizontal arrows.
More clear.
What?
Yeah, one's here on the right, one on the left.
Ah. This is the final proof anyway, so I can erase everything else. All right. So now we use snake lemma to show that.
You also need to check that the right are
Yeah. So, I mean, the exactness of the rows basically just follows from exactness of the sequence of chain complexes. But yeah, the idea is that once we have this giant diagram, we can construct this snake lemma map. Delta n exists.
Snake lemma actually is a little different, right? We had these were,
Kernels and co-kernels.
and those were arbitrary maps in the middle.
Yeah.
But like,
Yeah.
but that's the same thing because having a sequence with 4 ABCD and then 2 zeros, the exactness of that is equivalent to A being the kernel of the map in the middle, and D being the co-kernel. So like this is in fact exactly the type of diagram.
Right. So this delta n exists by snake lemma. But the only thing that remains is to check that the map that we'd constructed in snake lemma it basically coincides with this connecting homomorphism that we constructed in the previous theorem, which is true. But most importantly, the most important corollary of today is that the zigzag lemma is equivalent to the snake lemma. This is my favorite sentence in all of math. Proof the proof of this is based on just what we saw right now. The converse involves taking basically applying the zigzag lemma to a short exact sequences of complexes concentrated in just 2 degrees. Of the form zero kernel pi image pi 0. This map is pi, and similarly maps rho and sigma. So this ultimately implies by zigzag lemma, this implies a long exact sequence of homologies. It looks like this: 0 kernel pi, kernel rho, kernel sigma, co-kernel pi, co-kernel rho, co-kernel sigma, back to 0. And this is exactly the statement that we had from snake lemma.
Yeah, I don't know if that is 0 kernel. Why you taking?
Yeah. So this is just the most trivial exact sequence you can write, but you can still apply zigzag lemma to this, and that ultimately gives you this. So you can prove the statement of snake lemma from zigzag lemma. So snakes zigzag, and everything that zigzags is also a snake. That's it. There's still 10 more minutes. Alex, do you want to continue for the 10 minutes? All right. Finished
Do
it.
we have the syntax?
Well, I printed that last week and there's nothing since, there's just empty stuff on the last page.
What is the last page? This is the last page. Yeah.
Didn't realize I need to be printing it out incrementally in real time. Place, pause,